All right. Hello, everybody. It's Thursday, last day of April. Um, okay, so today I'm going to finish 15.3. I need to tell you about type 2 regions. That's not a big deal. That's the same thing as type 1, but flipped. And I'm going to do a few examples, and that will be it for 15.3. Okay. All right. So again, we've seen that if we have a type 1 region, we can use Fubini's theorem over this region. And actually, you know what, I'm not going to go through type 1 again. I'll just do it for type 2. It's the same thing. So let me just delete this. Okay, so this is something you've seen in Cal 2, by the way. So a region S in the plane is of type 2 if it has the following form. So it's the set of all pairs, all points x, y, such that y is between two values c and d, and x is caught between two functions h1 and h2, where obviously c is less or equal to d, and h1 of y is less or equal to h2 of y when y is between c and d. Okay, so the picture, so again, it's the same as type 1, except it's in the y direction. So it looks something like this. We've got c, we've got d, and we've got the graph of two functions, h1 and h2, which are functions of y rather than x. And the region S is everything here, right? So the way to view this is when you fix a value of y between c and d, then the points you're interested are those where x is between the values of h1 of y and h2 of y, okay? So the result for type 2 is exactly the same as you would expect, except it's in the other direction, okay? So here's the result, okay? I'm out of coffee. I'm back to tea, like at the college. Okay, so theorem. If S is of type 2, as above, right? Same description. Then the double integral over S of a function f can be computed as follows. So it's the integral from c to d, integral h1 of y, h2 of y, f of xy, dx, dy. So again, notice the non-constant limits of integration are always inside. It makes no sense to have them outside. Okay. So this is the same result as for type 1, but in the other direction. Okay. Just a remark, and this is something you've seen also in Cal 2. So there are many regions which can be seen either type 1 or type 2. Okay. Choose the most convenient. right? So depending on the situation, it might be better to express it as a type 1 or as a type 2, okay? So now I'm going to show you a few examples. Here's one which is a region you may have seen in Cal 2. So, okay. So here's our first example. Okay. So we're asked to find the double integral over s of x times y, where S is the following region, is the region bounded by the following curves. It's y equals x minus 1 and y squared equals 2x plus 6. Okay? So as opposed to the example we looked at yesterday, the only work you have to do here is basically just describe S in the proper way, and then you can just integrate. You don't have to do more than that. So, okay. So obviously here, I mean, it is theoretically possible to solve this without drawing anything. It is possible, but probably not a good idea. Okay. So let's just let's see what S looks like. It's easy. Okay, so I have a parabola and a line, so that shouldn't be too hard. Okay, so let's start with y squared equals to 2x plus 6. As you can see, it's the y, which is squared, so it's a parabola on its side, right? So I'll solve for x. So this is 2x equals y squared minus 6, or x equals 1/2 y squared minus 3. So I can see this as follows. So this is just the parabola x equals to y squared. It's halved, so it's a little bit more open. And then we shift by 3. So it looks something like this. Right? Okay. And then I have the line y equals to x minus 1, which is the following. Oh, maybe this goes here. So the line is something like that. Okay. It's all crooked, sorry. Okay, so the region S is right here. Okay. Is it type 1 or type 2? Well, it's actually both. Okay. So it is, you can see it as a type 1 region if you wish, but it's way more complicated to do it. It's much easier to see it as a type 2. Okay, so it's both type 1, type 2, but cleaner, easier as type 2. Okay, so what does that mean? It means that I'm going to look at segments like this, horizontal segments, and see what the endpoints, where they lie, on which curve they lie. And that's pretty clear, right, what the curves are. So the last thing is to find the values of C and D. And how do I find that? Intersection, right? So this is the only real work that there's to be done here, is the intersection points. So let's do that. Right? And since I'm looking for the values of y, I'll immediately state my intersection in terms of y, right? So I have x equals to 1/2 y squared minus 3, and x is equal to y plus 1. And so putting those together, I'm going to get that y plus 1 equals to 1/2 y squared minus 3, right? They're both equal to x. Can it still be a type 1 if on the left the slice touches the same function and not both? Yeah, so it is type 1, but it's a real mess to express it as a type 1. Let me explain a little bit more if you wish. So the parabola, so what you'd have to do is, yes, find an expression for the bottom part of the parabola and find an expression for the top part. So you have to solve for y, then you'll have the positive root and the negative root, right? And the bottom part will be in two pieces. It will be one piece is the parabola with the negative root, and the other one will be the, it's a total mess. I mean, it's possible to do it, but it's not a good idea, okay? But it's theoretically, I mean, if you look at it, right? The bottom part would be this part, like that. That would be the bottom function. But you see, it's nasty to write down, but it's legit, but not a good idea. You see what I mean? Yeah, okay. Yeah. So in any case, if you see that type 2 is the right way to do it, then that's perfect, right? That's fine. Okay. All right. So here you solve for y. I won't do it. You can do that. It's a quadratic. And you will find the values, where are we? Where are we at? -2 and 4. That's what you'll find. So this will be -2 and this will be 4. Okay, so these are the values of y where the curves intersect. Okay, so that means that S is the set of all xy such that y is between -2 and 4. Okay, and for a fixed y, right, what are the values of x? Look at the horizontal line. The left part is on the parabola, right? It should be expressed as a function of y. So this is 1/2 y squared minus 3. And on the right-hand side, you're on the line, which is y plus 1. Okay, so this is your h1 and your h2 functions. Okay, so this is the description of S as a type 2 region. Copy, not cut. Okay, so I want to compute. This is S, and I want to compute the double integral over S of x times y. So what is that? This is then the integral from -2 to 4, integral y squared over 2 minus 3 to y plus 1 of x times y dx dy. Okay. Okay, and then now it's just integration. Start with the inside part. Let's do that. So -2 to 4. I'm integrating xy with respect to x, so this is x squared over 2y, evaluating between y squared over 2 minus 3 and y plus 1. Okay. So I replace, subtract. So this is integral -2 to 4 of y plus 1 squared over 2 times y minus y squared over 2 minus 3 squared times y dy. Okay. I won't finish the computation because from this point on it's straightforward polynomial, we just expand, integrate. Okay, so I'll just leave it here. This is straightforward. And you should be getting 36. Okay. So far, so good. Hopefully. Yes, good. All right, next. So 2 more examples. The next one is a slightly more involved. We're asked to find the volume of a tetrahedron which is bounded by the following planes. So here are the planes: x plus 2y plus z equals to 2, x equals 2y, x equals to 0, z equals to 0. Okay, so again, the name of the game is always we need to set up the double integral of the right function over the right region, right? Need to express this as double integral over some f, s of f, find f and s, right? That's the game, okay? So here it's not a bad idea to try to draw this. Now, this might look a little daunting, but here's a trick which is very useful. So I want to see the plane x plus 2y plus z equals to 2, okay? So this thing is not vertical or horizontal or anything, so it's going to cut the 3 coordinate axes somewhere. So I can draw this triangle and actually visualize the plane, okay? So intersect with 3 coordinate axes. Okay, so what are the coordinate axes? Well, you set 2 variables to 0, and this is what you're going to get. So if x equals y equals to 0, then here I'm going to get z equals to 2, right? So it means that the point 0, 0, 2 is on the plane. Okay, if I set x and z equals to 0, you're going to get y equals to 1. So 0, 1, 0 is on the plane. Okay, and if you set y and z to 0, you're going to get x equals to 2. So 2, 0, 0 is on the plane. So let's see what this gives us. So z is 2. We have this point, y is 1. We get this point, and x is 2. We got this point, right? So now you can actually see the plane by how it intersects like that, right? So it cuts the first octant this way. Okay, so this is very useful. Okay, so that's clearly one, I mean, not quite, but it might be one face of the tetrahedron. So what are the other planes? There's x equals to 0, so I have the back face over here, like that. Z equals to 0, so we have the bottom part like that. But the other one is x equals to 2y. And that's a bit annoying, okay? So need to see the plane x equals to 2y, okay? But So Z is free, so this thing is vertical, right? So you just look at the line x equals to 2y in the plane. So C line x equals 2y in the xy plane, and extend, so Z is free, right? So x equals to 2y, that's y equals x over 2. So it's something like that, right? So it'll extend up, right? So the tetrahedron that we're looking for is actually here. That's the guy. Okay? So that's my tetrahedron. So I'd like to see how this is a double integral, where what's the top part? What if you look at all the vertical lines that go through this tetrahedron, what's the part they get on top? It's that first plane we looked at. Okay, so top is plane. It's x plus 2y plus z equals to 2, right? And that's the same as z equals to 2 minus x minus 2y, right? That's the graph of a function, f. That's our f, right? So if I integrate f over the base of the tetrahedron, I'm going to get the volume that I want, okay? So we found our f. So now we have to find s. That's the base of the tetrahedron, which is this part right here. Okay, so to find this, now I don't need to look at the 3D version. I'm just going to look at what's happening in the plane. Okay, so to find S, let's look only at what happens in the xy plane. Okay. It's cold. Okay, so let's see. Okay, so again, the planes that I'm given are x plus 2y plus z equals to 2, x equals 2y, x equals 0, z equals to 0. Sorry, I'm going to go back and I'm going to just copy this. Okay, so okay, so what do I mean by top? Okay, I mean that if you take any vertical line that goes through the tetrahedron, right? When you're going to go outside the tetrahedron, which part of the tetrahedron are you crossing? It's that flat part on top, right? Which is given by x plus 2y plus z equals to 2. So I want to see this as a double integral of the graph of a function, right? So the top should be the graph of a function. And I want to find this information here by looking at the tetrahedron. So if you're inside this tetrahedron and you go up, you look at the ceiling, what plane are you looking at? It's the x plus 2y plus z equals to 2 everywhere. That's the ceiling. Does that make sense? Maybe not. Yes. Okay. Yes. 3 little dots. Okay. I don't know how to explain it in any other way. So again, if you're inside the tetrahedron and you look up, what part of the tetrahedron are you looking at? It's that bounding plane, which is given by this here. That's what I need to convey. Sorry, I can't find another way of explaining it. Can you sort of visualize the tetrahedron a little bit? What is in front? Yeah, sure. I mean, it's not the whole plane, but okay. So let's try. Okay, let's try it another way. You're in the XY plane in coordinates XY. Okay, and you look up, and you want to know what's the height of the ceiling right above you. What's the Z coordinate of that point on top? It's given by that equation right there. X plus 2y plus Z equals to 2 is going to give you the height of the ceiling if you're standing at the point XY. Ah, great. Yes, excellent. Okay. The first equation is the equation of the tetrahedron is the solid bounded by the 4 planes. That's what the tetrahedron is. Okay. These are just 4 planes. They give you the 4. Why isn't F the equation? Sorry, I don't understand your question. There's no equation of the tetrahedron. We just have 4 planes, and what's inside is, I mean, that's the solid. So I'm not sure I understand. Okay. All right. Okay. So again, what I want to do now is to find the region S, okay, which is that triangle right here. So I'm going to draw that triangle in the XY plane. Okay. So I'm going to, so I have to find what these lines are. So this line here, that's the easy one. That's X equals to 2. I mean, it's easy because we drew it knowing this is X equals to 2y, so it's over here. Right. And now, what is the other line that's going this way? So so this is the value 1. This is the value 2. So it goes from, it's something like that, right? So I want to know, and the region S is this. That's S. Right? I'm just redrawing what was in my plane over there. I really have to think about it. It's just, you have to switch things around. Okay? So now I look at this S, and clearly it's a type 1. I mean, it's easy to see as a type 1 region. Okay? So natural type 1. Okay? So I have a line on top and a line at the bottom. So I have to figure out what the equations are. So what is this line here? How is it obtained? If you look at the picture, it's where the plane X plus 2y plus Z equals to 2 meets the XY plane. Okay, so this is intersection of X plus 2y plus Z equals to 2 and XY plane. Right? So how do I find that? Well, if you're intersecting with the XY plane, you set Z equals to 0. Right? So we're going to get X plus 2y plus 0 equals to 2. So that's the equation of that line. Okay, so let me redraw that. I have this, I have this, This is S. This is x plus 2y equals to 2. And this one is x equals 2y. Okay? So I want to see this as a type 1 region. Sorry, my picture is really bad. Right? So I know what the top part is, I know what the bottom part is. What remains, well, obviously here our a value will be 0, and the other thing that remains to check is what is the value of x over here, right? So it's the intersection of the two lines, okay? So I've got x plus 2y equals to 2, and x equals to 2y. I want to find the x value, so I'm going to get x plus x equals to 2, so x equals to 1. Okay? Hopefully things are okay for you guys up to now. And this is 1. Okay? So I'm trying not to change slides, that's why I'm flying all around, I'm sorry. But so as a type 1 region, S, this triangle, that's the set of all points such that x is between 0 and 1, right? And what is y? If you fix a value of x, you want to know what is bounding the values of y, right? But we know this is, so there's the line on top, x plus 2y equals to 2, right? So that means, so I'm going to solve for y, so that's 2 minus x divided by 2. And on the bottom part, x over 2. Okay. It's just little things. It's not if you're hopefully you've done enough of this in Cal 2, and hopefully it's not too far away, even though some of you have burnt your lecture notes. But think about it a few minutes, it's not so bad, okay? It looks messy right now, but okay, so everything together, I need to copy this. So finally, so the volume will be the double integral over this S, of which function? Well, our f we saw earlier, I have to go back, 2 minus x minus 2y. That's my ceiling. Okay? 2 minus x minus 2y. Okay, so that's my volume. And it's a type 1 region. So now I can compute it this way, integral 0 to 1, integral x over 2 to 2 minus x over 2 of 2 minus x minus 2y dy dx. Okay? And so, again, start on the inside. So this is, I'm integrating with respect to y, so this is 2y minus xy minus y squared between, so it's from x over 2 to 2 minus x over 2. Okay, I'm going to substitute and subtract. is sort of longish, but not hard. So this is 2 times 2 minus x over 2 minus x times 2 minus x over 2 minus 2 minus x over 2 squared minus, I need 2 lines, the same thing, replacing by x over 2 like that. Okay, and again, you get just a big polynomial in x and have to expand. You can simplify if you wish, but again, I'm not going to do the computation. And you will find 1/3. Okay. So you have a volume to find. You need to find which function to integrate over which region. You may have to play around with things. As you saw, you have to mess around a little bit with equations of planes and whatnot. Express your region S as type 1 or type 2, and then compute the integral. Okay, there's a lot of little things. Okay, but if you do exercises, examples, and if you're stuck, you don't know exactly, just let me know. I'll unstuck you. Okay. So hopefully this is not too bad. I feel really alone right now. I feel really, it's just talking to my machine. It's just awful. So far so good. All right, good. Okay, so I have one last example, which is much shorter, much less computational. It's a little bit different, but it's a really important example. So here it is. Classic problem here. So evaluate integral 0 to 1, integral x to 1, sine of y squared dy dx. So here, I mean, it looks like it's easier than everything we've done so far because we don't even have to find f or s or express it. It's all already done, right? All we have to do is compute the integral. So there's a catch, right? So what's the catch? And the fact that you did Cal 2 a year ago is even worse because if you were right in the middle of Cal 2, well, let's say near the end, but doing Cal 2, there would be a much better chance that you see the catch. The catch is that you can't integrate sine of y squared. There's just, it's one of those functions that doesn't have what we call an elementary antiderivative. So you can't find a function, write it down, such that its derivative is sine of y squared. If you remember the integration by substitution, right? What's missing from when you want to integrate sine of y squared, there's this y squared inside the sine. What you need outside as a factor is y, right? This is, so this is not good. Okay, so no antiderivative. I'll put that in quotes because there is an antiderivative, it's just we can't write it down. So it's something, it's different. So it's not an elementary function, okay? So integral of y sine y squared would be easy. Okay, substitution. So the catch is hard to see, especially if it's been a year since you haven't done any sort of integration, okay? So what's the trick here? So there is no way you can integrate first inside. It's impossible. So, okay, it's a double integral. And we saw by Fubini that somehow we can switch things around, right? But I also said you just can't put those non-constant bounds outside. You can't do that. So how do you switch? Okay, so must switch order of integration, but you have to do it correctly. Okay, this is important. So here's the part, so this is the part of the problem which is really interesting and important, is that I'm going to use those results that we saw, just the type 2 and type 1 results that tell you how to compute the integral. I'm going to use them in the reverse direction. Okay, so here's what I mean. So integral 0 to 1, integral x to 1, sine of y squared, dy dx. What is that? That's the double integral over a certain region S, sine of y squared. What is S? Okay, so you see what I mean? I'm using the thing backwards. So in the previous examples, what we did is we had a region S as type 1 or type 2, and we expressed the integral as an iterated integral using this. So now I'm going the other way around, okay? So what is S? If you look, here we're going from 0 to 1 outside. These are the x values. Right? So this means that S is the following. X is between 0 and 1, right? 0, 1. And you look now here, the y goes from x to 1. Okay? So if you're not sure what I just did, go the other direction. So look at the right-hand side. We've got S, which is a type 1 region, right? And our results said, well, if S is a type 1 region, then the double integral over S can be computed as an iterated integral exactly this way. Okay? So that's all I'm doing. So I haven't switched things around yet. So now what I want to do is I want to look at S. What does it actually look like? Okay, so let's see what S looks like. Okay. So this is S. All right. So what is that? Okay, so X is between 0 and 1. And once you fix X, Y should go from X to 1. So this function, this is your G1 of X equals to X. This is your G2 of X equals to 1. So what is G1 of X equals to X? Its graph is this, right? And G2 of X equals to 1 is a constant function 1. That's this one, right? So this is S. Right? So X between 0 and 1. If you fix an X, the least value for Y is X and the top value is 1. Okay? So I want to flip the order of integration. So what I'm going to do is to express that as a type 2 region. Okay? So what is this as type 2? Okay? Well, is the set of all xy such that, so y should be between constant bounds. Here it clearly is between 0 and 1, right? And what are the values of x? So if you fix a value of y, you look at the possible values of x, that segment, it goes from 0 to y, right? That's S as a type 2 region, okay? So our original integral, which was this, we know it's equal to the double integral over S sine of y squared. And by the type 2 result, now I can express it as the integral from 0 to 1, 0 to y, sine of y squared dx dy. Okay? So what did we gain? Well, now we can actually integrate the inside part. It's super easy because it's an integral with respect to x, and the sine of y squared is just a constant, right? So now this part is easy. Okay? So I'm going to switch slides here because I don't have enough room. I'll take a little sip of water. Okay. All right, so this is integral 0 to 1. Now integrating with respect to x inside, so this is just sine of y squared times x between 0 and y. Right? So I just substitute, subtract. So this is y times sine of y squared minus 0. Okay. And now I'm happy because the integral I'm left with is now doable because I have that nice y, which is basically the derivative of y squared. You just use a substitution, right? You can use, let's say, u equals y squared. The du is 2y dy. Divide by 2, I'll just do it directly, right? So derivative of cos is minus sine, so I need a minus cos. And there must be a half factor here so that everything turns out okay. If you differentiate this function, right, derivative of cos is minus sine, the minus signs cancel out. And derivative of y squared is 2y, so the 2's cancel out, and I get exactly what I want. And so this is minus 1/2 cos of 1 minus cos of 0, which is 1. So this is 1 minus cos 1 over 2. Okay? The point of this, so it's cute. If you understood what happened, it's like, it's a really cute trick to get around an integral which is not possible, okay? But the main point is really to understand how both double integrals, the iterated integrals, are related to the same region but expressed as type 1 or type 2. Okay, so this is, so there's a lot of the things that we've covered are contained in this example. Are there any questions, comments? It's so lonely here. Nothing. Times 17. I'm not sure. I don't understand your question. Is a gradient the tangent line of a surface? Okay, first of all, a surface, you can't talk about the tangent line to a, yes, that's better. Yeah, we know the gradient. If you have a surface which is of the form, let's say f of x, y, z equals to 0, then you know the gradient of f at a point will give you a vector perpendicular to the surface at that point. That's for free. Okay? Now, for the parametric equation of a line, we saw that much, much, much earlier. If you have a vector parallel to your line and a point on that line, you can find the parametric equation of the line, right? Oh, but you're looking for the tangent plane, no, for that problem? But then your gradient gives you the normal to that plane. That didn't look right. But anyway, yes, so you have a surface given by f of x, y, z equals to 0, and you have a point on the surface, then the gradient of f at this point is perpendicular to s. So that would be a normal to the tangent plane, right? So if you have the point, you have the normal, you should be able to find an equation for the tangent plane. Does that answer your question? Good. Any other questions?
I was wondering, what's the best way to rotate a vector for a certain amount of degrees? Because there are some problems in the WebWorks where we need to find the derivative of a vector like 45 degrees away from the gradient. So what's the best way to find this vector? Like to rotate the vector of 45 degrees.
You just need to use the dot product with the norms, and you can plug in the angle.
Did you hear that?
Yes. The dot
Does it help?
Well, I guess I can figure it out with that.
Yeah.
Okay. Thank you.
Okay. Other questions, comments? I did that, but I'm still unable to solve problem 18 as well. I haven't memorized the okay, I've got it here. Number 18. So A or B, that's giving you trouble. B, I suppose. Yeah. Okay, so if you answered A correctly, then okay, I see what you're saying. You're saying that you got A right, but it still didn't help you to find B. Okay, there's a couple of ways you can do it. So for number 18, you can do it with the early version with the partial derivatives and the linear approximation, you can do it like that. I would use what we saw later with the gradient. So the surface z equals to x squared minus y cubed. You can rewrite that. I mean, okay, you don't have the same surface that I do, but I've got z equals to x squared minus y cubed. That's the same as z minus x squared plus y cubed equals to 0, right? Call this f of x, y, z, okay? Then you know this, you know that the gradient of f, so now here in my problem, they have x, y equals to 4. So then I'd find z, okay? So z minus 4 plus, oh, that's annoying, 64 equals to 0. So z would be minus 60. So the gradient at 2, 4, minus 60, unless I made a silly mistake, is perpendicular to the surface at that point, right? You use the pane to find the equation? Yes. Yeah, that's great. So if you find that, that's your normal, right? And so the general trick is always this: if you have your normal n, you locate it at the point P0. If you take any point P on the plane, n dot P0P is 0, right? That will give you the equation of your plane. Can't go wrong. Right? So if this is x0, y0, z0, and this is your generic point x, y, z, it means n dot this is 0, right? How did I get 2, 4, minus 60? I was given the point x, y equals 2, 4 in my question, and the surface is z minus x squared plus y cubed equals to 0. So I substituted the x and y they gave me. I may have made a mistake. 4 cubed is 64. All right, good. You found it. Excellent. Okay. Very good. Anything else? Any? All right. So if that's it, I'll. You can't get number 17. Want me to do it for you? Yes, please. That was a joke. Okay. Consider the line perpendicular the line to the surface blah at the point blah. Find a vector parametric equation for this line in terms of the parameter t. Okay, so I'm not going to do it, but okay. Okay, so we're talking about the line perpendicular to the surface. Here I'm given z equals to x squared plus y squared. It could be the same as you. At the point where x is minus 4, y equals to 1. And they want a parametric representation of this line. Okay. So to find a parametric representation of a line, I need two things. I need a point. That should be easy because of this. And I need a vector, let's say V, parallel to the line. And once I have these, then my R of t is TV plus P0, right? That's from first couple of weeks, okay? So with the point should be easy because they give me X and Y. I can find Z. Yeah. Okay. And for the vector, well, we know that the gradient is perpendicular to the level surfaces. So express your surface as a level surface. Z minus X squared plus Y squared equals to 0. This is f of x, y, z. Gradient of f at the point you're interested in is perpendicular to surface 0. That's all. It's always that. Does that help? Just say? Yes, okay. All right. Other things, other questions? No? Okay. So if there are no, yeah, same to you. I will, I'll stop the recording and post everything, and I'll see you next week. Cheers.